Take a walk with me through an ancient, verdant land. So vivid are the colors and aroma of the entangled fauna that it takes you an age to notice something isn't as it should be. It's all quiet. The near absence of birds and mammals is the only indication that this land is dying. Its fate sealed by the ending of an ice age. Waters are rising. The lush landscape below your feet will soon be 30 meters below the surface of the Pacific. Any species able to migrate have escaped to continue their fight for survival in a warming, shrinking world. Those given life by their roots are held to perish by them. What is happening here? What can we learn from the history recorded deep in the melting polar ice is of vital importance, because right now, it's happening again. What is causing the ice caps to melt in the present? How will it affect the most powerful climate systems on Earth? And what hidden dangers does the ice contain? I'm Alex McColgan, and you're watching Astrum. Join me today as we look at what makes ice such an interesting and crucial feature of our planet, and imagine a future wetter Earth, one whose existence may have already been forged. On Astrum, we love to explore gigantic objects in our universe whose scale through time and space stretch almost beyond our grasp. Look up towards Cassiopeia, and there is our closest galaxy, Andromeda. 2.5 million light years away, 200,000 light years from edge to edge. Yet, despite its magnitude, we can connect to it. So it's curious to me that looking only 80 years to our future feels too distant to connect with, to understand that things we do today affect tomorrow's world. So, let me take you there. At the beginning of our journey is the ice. Ice is a remarkable substance, one that can store vast amounts of energy. As a comparison, energy stored in modern electric cars capable of accelerating tons of metal to over 160 kilometers per hour and carry both it and you hundreds of kilometers, could scarcely melt ice that would fit on its back seats. The energy storage capacity of ice is a large part of the reason that the climate has been so stable for the past 12,000 years. The ice is acting as a buffer against extreme temperature rises and falls. The Holocene has been a unique period in Earth's history for another reason too: the rise of human civilizations, made possible through the development of agriculture. The Antarctic ice cap first formed around 37 million years ago, the Arctic 2.7 million, as old as the light reaching us from Andromeda, and both caps are important for our stable climate to this day. Their historical size has largely been defined by Earth's position and tilt in the solar system, movements that affect the amount of energy that our planet receives. These movements are known as Milankovitch cycles, which I've covered in a previous video. According to these cycles, the ice at the poles should be increasing. We should be heading into an ice age. The sea levels should be falling as the ice caps get deeper. But instead, the polar ice is melting. Massive amounts of energy are being absorbed by the caps, and not only are we going in the opposite direction that the Milankovitch cycles predict, the ice loss is accelerating. Should all the ice melt, we are facing a 70-meter sea level rise, which will flood all coastal cities on the planet. Fortunately, that degree of ice loss is exceptionally unlikely, but we do need to know how much sea level rise to expect so that we can plan ahead and protect Earth's ecosystems. To predict just how much, we need to understand why and how the ice is melting. We know the release of greenhouse gases is a driver of today's global warming, overpowering the Milankovitch cycles, causing the ice caps to melt and the sea level to rise. But I was astonished to find out that this hasn't always been the case. Detailed records kept in the Antarctic ice core reveal that in the past, it was increasing temperatures that caused increasing CO2 levels. cause and effect were flipped. But isn't that a blatant contradiction? Well, actually, no. Each positively influences the other. It's just a case of which happens first. We see this play out as the increased temperatures of today's climate thaw the permafrost around the Arctic Circle, releasing long-stored carbon reserves, which in turn accelerate further global warming. The mechanism by which increased CO2 and temperature affect the polar regions reveals a complicated and fascinating climate system. Greenhouse gases trap infrared heat radiation emitted by the surface of the Earth. This heat is retained by the atmosphere and the ocean. Around 90% of the energy increased is absorbed by the ocean, which is no surprise given it has almost 250 times the atmosphere's mass. So, where does this extra energy go? Well, as anyone who's touched a hot stove or licked a ski lift chair knows, heat moves from hot things to cold things. So it makes sense that it is at the cold poles where we see many times the average global temperature increase, because that's where the temperature gradient demands that the energy flows. And it's flowing there primarily through the ocean currents. Because of its density and heat capacity, water is very effective at transferring energy. That's why water is used both as a coolant in cars and a heating medium in homes, and why air, with a low density and low heat capacity, is often used as an insulator. That difference allows you to sit comfortably in a 90°C sauna for many minutes, while you'd reflexively be unable to insert past your fingertip into water of the same temperature. Other factors play a role in melting the ice too, like the albedo or whiteness of the ice. Soot darkens the surface of the ice, causing it to absorb more energy from the sun. Air quality measures are reducing particulates in the atmosphere and on the ice, meaning we will see less melt from ice directly absorbing the sun's energy. But the lowering of particulates in the atmosphere also blocks less sunlight overall, so more energy reaches the surface, accelerating the greenhouse effect. I told you it's complicated. Let's explore the ways the oceans are melting the polar ice, as it is happening right now on the West Antarctic ice shelf, a particularly vulnerable area. It contains ice in several forms. Sea ice is very seasonal and is responsible for the doubling of Antarctica's area through winter. This ice melts through contact with the ocean as ice cubes do in a cocktail. The direct impact of all the sea ice melting would only contribute a few centimeters to sea level rise, but its importance lies in its role as a barrier to the otherwise exposed ice shelf. The sea ice insulates the oceans from atmospheric warming and keeps the humidity and temperature of the air above it low. Being fresh and white, like the most fairy tale of glistening winter flurries, it also reflects a large portion of sunlight back into space. When this sea ice is low, it exposes the ice shelf, which protrudes almost all the way around the Antarctic. These floating ice shelves can be gigantic. Some, like the Ross and Ronne-Filchner shelves, are greater in area than my home country, the United Kingdom. The warm seawater eats at the underside of the shelves. Huge icebergs the size of our biggest cities can break away as it weakens and drift as far as Africa. Since these ice shelves are melting, they also contribute minimally to the rising sea levels. But it's what the ice shelves hold back that has the most potential for sea level rise. As the shelves shrink, the main body of sheet ice that sits atop land is more exposed, allowing faster flow rates from glaciers and ice streams. But don't be fooled, these ice streams are far bigger than their name would suggest. Incredibly, some are as wide as the mouth of the Amazon, hundreds of kilometers long and kilometers deep, all flowing towards the sea. Feeding these streams is the colossal ice sheet itself. Since the ice sheet is supported on land, the mass of ice melt leads to a direct increase in sea level. These ice melting processes are natural phenomena and would still occur without global warming. The poles take fresh snowfall and ice formation every year, which adds to the mass of the ice. And just for them to retain at their current size, we would witness sea ice melting, ice shelf carving, and glacial flow. Although, at this very moment, Earth's polar ice sheets are far from equilibrium. The rate at which they are losing ice is quicker than fresh snow can fall, meaning that they are shrinking. Because of the extra energy in our oceans and in the atmosphere captured by greenhouse gases, we are already committed to significant ice sheet loss. Can we say how much sea levels will rise from the melting alone? If you thought it would be a simple case of calculating the volume of ice lost and adding it to the volume of water in the seas, well, you can join me in being wrong. To arrive at an accurate estimate, we need to understand a few other interactions. We tend to think of Earth's crust as solid, but given enough force, the Earth will change shape too. As the ice melts, the continental plate that supports it bears less weight and rises up above sea levels, while at the equator, the coastal land shrinks into the sea, creating localized sea level falls and rises. But the single biggest addition to sea level rise to date required no additional water, and was simply due to the thermal expansion of what was already there. Around half of the sea level rise we have already seen since the Industrial Revolution has been due to this expansion. This process is easy to calculate, and we know how it will contribute to sea level rise in the future. However, the deluge of cold, fresh water being dumped into the salty sea has other, less predictable consequences. Remember, Earth systems are dynamically intertwined. A feature of these dynamic systems is that they are vulnerable to dramatic changes in behavior, known as tipping points. As with playing Jenga, the tower becomes less and less stable as we mine the lower levels for material to build even higher. Eventually, merely touching the next brick brings it crashing down. This would cause a very rapid phase change. One tipping point that could occur within our lifetime is the slowing of the Atlantic meridional overturning circulation. This is an oceanic flow, a powerful energy transfer system. Should it weaken or collapse completely, sea levels on the eastern seaboard of America could rise by up to 1 meter. But in Europe, coastal waters would recede. However, Europe would face other, more extreme consequences. Around the world, rainfall patterns would change drastically, pushing some ecosystems to become rainforests, while pushing others towards desertification. To understand how all of that is possible, let's look at how the AMOC functions now. The AMOC is part of the thermohaline circulation system. It is driven by changes in heat, thermo, and salt concentration, haline. The AMOC brings warm tropical waters up past the United States and across to Europe, helping to make Northern Europe warmer than it ought to be considering its proximity to the polar circle. As these waters continue north to the Arctic, it is partially frozen into sea ice, which leaves cooler, saltier water to sink to the bottom of the ocean, where it then flows back south to complete the cycle. However, the melting of the Greenland ice sheet is inundating the northern part of the AMOC with fresh water, diluting the seawater, making it less salty and less dense. This makes the gradient directing the water to sink to become shallower, slowing down this part of the cycle and reducing flow, just as a slow middle lane driver on the motorway can cause a tailback, stretching frustratingly far back across all lanes. The slowing down of the AMOC backs up water on the American East Coast and reduces the flow to Europe, meaning that sea levels would rise in America while Europe would be spared, though that's little consolation to a continent that will lose much of its way of life and food production capacity through cooler temperatures. The UK alone is facing an average temperature drop of 10 degrees Celsius, which would make it colder than Iceland now. The melting Greenland ice sheet also contains organisms that we haven't seen on Earth in hundreds of thousands of years. When a new predator travels to an ecosystem not evolved to live with it, it can upset its delicate balance. This is also true of a pathogen traveling through time. Most of the species will be harmless, but as we saw in 2020, it only takes one black swan to change everything. With more cells being released from ice melt each year than there are grains of sand on Earth, the risk one is a black swan is significant. A risk that increases with the depth with the permafrost thaw. The further back in time a potential pathogen is from, the bigger the jump in its genome and the lower our ecosystem's readiness for it. So, the world is changing. As we have seen, ice is an incredible recorder of Earth's history. Through studying its secrets, we can see Earth's past. Just as the ice cores detail Earth's ecosystem as the Bering Strait flooded, it contains our history too. As the ice melts, it replays many of humanity's environmental missteps by re-releasing trapped chemicals we have produced. CFCs stored in the ice can again deplete the ozone and accelerate Arctic ice loss. Chlorinated pesticides, many long banned from use, can find their way back into Earth's ecosystem, some of which will have been made even more potent by their time stored in ice. Vaporized lead from the use of leaded petrol will also be re-released as the ice layers that contain it melt away. This chemical cocktail adds yet more stress to a global ecosystem moving ever closer to an invisible edge. When we add all these factors together, the year 2100 could look very different. Exactly how different is under our control. The current predicted average sea level rise is 0.5 meters. That doesn't sound like much, does it? A map of the world's coastlines would look almost unchanged. However, it's not the averages, but the black swan events. The storms, the floods, the heat waves that drive human behavior. By the year 2100, a population the size of the US will be exposed to regular coastal floods. Faced with increased risk, where will Earth's coastal populations move to? How much will our way of life change? The rich diversity we see in cultures and species on Earth is born out of adapting to the environment. Both humanity and life itself have demonstrated time and time again that they are irrepressibly adaptive. Humanity can and has to learn from its past and look to the future. So there is hope. While the melting ice reminds us of the environmental damage we have been responsible for since the Industrial Revolution, it also reminds us of how often we came together to make a change for the better when we understood how we were affecting our planet and ourselves. I believe we can and need to do it again. It may well be that some engineering might be in order in Earth's future, to design and then build the technology that eases the pressure on the planet's ecosystems. Creating something that helps the planet might seem like a tall order, something only a brilliant inventor might accomplish. But have you considered that brilliant inventor may just be you? But Alex, I hear some of you say, I don't have the technical skills to accomplish something like that. Well, maybe that's true, but would you like them? Thanks to Brilliant, the sponsor of today's video, it's possible for anyone to get a grasp on engineering or other STEM subjects at beginner, intermediate, or advanced levels. Brilliant's online interactive courses have been proven to be one of the most effective ways to learn STEM skills, with bite-sized lessons that are 6 times better for learning than simply listening to lectures. Brilliant can help you develop skills and knowledge that can enhance your career options or better your understanding of the world. Click my link brilliant.org/Astrum or scan my QR code to get everything Brilliant has to offer for free for the first 30 days and then 20% off the premium annual subscription. Thanks for watching, and thanks to our crew of Astromnauts over at Patreon who help us make science knowledge freely available to everyone.
Chasing the algorithm can be hit and miss sometimes, so your contributions help us keep making the content we love. And if you haven't already, but you want to join the Patreon, there's never been a better time to get in on the party. Just sign up with the link in the description. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Once again, a huge thank you from myself and the whole Astrum team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.